Alright guys, we're going to start off by calculating Ernest Rutherford's chemistry grade. So on his daily work he got an 80%, and then on his lab he got 50%, and on his on his major grades he got a 95. So let's go ahead and see this now. You know in chemistry that your daily is worth 20%, right? And your lab is worth 20%. And your major is worth 60%. Okay, so let's see if we can color code this. What we're going to do is we're going to calculate a weighted average. You can't just average the three of these together. You can't, add these up and then divide by 3. That doesn't give you the correct weight. We need the right percentages in there. So what you do is you just take the 80 and you multiply it by 20%. So this is going to be 0.2 or 0.20, which is 20%, right? All you have to do is move the decimal over 2 places. So that is your daily grade. Now for your lab grade, you're going to take, doesn't look like he turned in all of his labs, so that's unfortunate. What he's going to do is we're going to add that to his lab grade, which is 50, and we're going to multiply that by 20%, or 0.2. Then we're going to add it again, you guessed it, to this one. He is a stellar test taker, maybe missed 1 or 2 questions, so he's got 95 times 0.60%. So those all add up to 100%, so we're all good to go here. When you calculate that out, we look at 80 times 0.2, and we're going to add it to 50 times 0.2, and then plus 95 times 0.6. See if I can turn on the light and maybe enlightened. So, and Ernest Rutherford scored an 83 on his final average. So even though he smoked the test and he even turned in some of his daily work, nothing kills your grade like a missing lab report. So I'll take this opportunity to tell you guys that those lab reports do mean something. That even though they're 20% of the grade, they still do count a lot. So let's see if we can get into what this is. So we're going to look at the relative atomic masses. Now, down at the bottom of our notes in page 8, we'll see that since the masses of atoms are very small, it's convenient to use relative masses. Okay, so oxygen 16 has a mass of this, and this is really cumbersome. Okay, so we don't want to use this anymore. We want to use something that's a little bit more, a little bit less numbers. Okay, so we know that what we do is we pick 12 grams of carbon-12, right? Remember, we learned about isotopes already. We know that carbon-12 has a mass of 12 AMU, right? Well, that AMU comes from that. So we find that we have 12 AMUs in carbon. Well, we base everything off of carbon, and that's where we get the AMU. So one atomic mass unit is defined as 1/12 the mass of a carbon-12 atom, or the mass of one. Yeah. Do you see how that works? Yeah. That's what you kind of need to know. You need to know how this definition works, and if not, just memorize it and you'll be fine. Okay? Now, so that's where we get the words AMU. Now, AMU does not have units, but if you ever see the letter U right here, that's what I'm talking about, is AMU. Now, that's atomic mass units. Now, so we have these different isotopes, but some of them appear more often than others. So if we need to calculate a weighted average to find the average atomic mass. Okay, and by finding the average atomic mass, that is actually going to be the mass on the bottom of your periodic table. That's how they're finding those, and that's why you don't actually have your. That's why they're not, exact numbers. That's why they don't. That's why they have a lot of decimal places, is because you'll have something that's like copper 63. You have copper 63, and then you have copper 65 right here. I'm going off of these examples down here. This one occurs more often. It occurs roughly 69%, and this one occurs roughly 31%, roughly. So you will get more copper 63 than 65. So your mass is going to be somewhere in the middle, and it's going to be a little bit closer to 63. So it's going to be 63.8 something, maybe. Okay, so it's, see how that works? So that's going to be your average atomic mass. So that's just us working it out. Now we'll actually really quantify it out in a couple of examples. So these are really easy to do, especially if you have some color codes. So copper has two naturally occurring isotopes, copper 63, which is 69.17%, and copper 65, which is 30.83%. We're going to calculate the average atomic mass of copper if the relative masses of the isotopes are copper 63. Let's see, 63 was blue, right? And it has a mass of this. Remember, that's off of the relative carbon, okay? And then copper 65, it has a relative mass of this, based off of that carbon 12 we have, okay? That's like a relative amount. Now, so what we'll do is we'll just take our mass, our blue mass, and we'll take it 62.94, and we'll multiply it by our percentage. Now, this needs to be a decimal, so we'll make it 0.6917. Okay? All I did was move the decimal place over to the left twice. Now we'll add the other one. We'll take our mass of our copper 65, 64.93, and multiply it by our percentage, 0.3083. Then we'll find, then we'll just type it all in the calculator. Easy enough. 62.94 times 0.6917 plus 64.93 times 0.3083. And lickety split, we get 63.55 AMU. Excellent. That's what we wanted to get, and I wasn't too far away when I guessed right here. I did guess that it would be somewhere between 63 and 65, and it would be a little closer to 63. So perfect. Now the average atomic mass of an element is found on the periodic table. So what you can do is you can know these atomic masses here, or you can know your masses, and you can actually identify the element just by looking it up on the periodic table. All right. Now, let's do example 2. So the same thing is going to happen here, except you have your isotope name. That's just the name. We're not going to really use that. We're just going to look at the mass and the abundance. All we're going to do is convert these to decimals. So you can convert these to decimals if you want, or just do it in your head. And we're going to multiply this number times this number and add it to this number times this number plus this number times this number. I'll go ahead and write that one out. This is the blue one, 27.98. Once that's all done, we now will type it in the calculator and we'll find our answer. Okay, so it's 28.09 AMU. So now you ask yourself, does this make sense? Well, most of it was silicon 28, right? So most of it had a number very close to 28. So your number should be close to 28. Now it will be a little higher. That's because you have some heavier elements here that are weighing it down just a little bit. But most of it is silicon 28. Okay, so pretty easy. Your examples in Schoology will involve a little bit more algebra in here. If you involved an x in here and you were given the atomic mass, you would have to solve for x instead. But that's really essentially the only little trick that's going to come up. Okay, so I hope y'all have a wonderful day.